Okay, let's take a look at the problems you want to know for our final. First topic we're going to look at is limits. So these ones, each of the first few problems are all going to be over like 10 points each. So these ones you can think of as like 3 points each with, as long as you're doing something with it, you're going to pretty much start with a free point. Remember, limits to infinity, you're going to look at dominant terms. So if I take a look at this guy, I've got to think about what the dominant term is going to be. Well, I'm going to have the square here, and when I do 2x squared, I'm going to get 4x squared. This negative 16 is not going to do much, so I get like 3x. On the bottom, I'm going to have 3x squared times negative x. That's going to give me negative 3x cubed. So I'm just kind of figuring out what each part is doing. Now, I could say this is equal to 12x cubed over negative 3x cubed. And then, of course, the x cubes will reduce. 12 over negative 3 will make this go to negative 4. But this is kind of the important step when we started right here, just thinking about what will be the dominant term. So now we're going to do the same thing. Again, we have a limit to infinity. So dominant term on top is pretty easy. That's 5x to the fourth. On the bottom, I'm going to end up with negative 2x times x, which is negative 2x squared. Okay, so now I've got dominant term on the top. So now I've got to decide, is this going to go to infinity or negative infinity? Well, this is going to reduce to 5x squared over negative 2. And as x goes to infinity, this gets to be really, really big. But because of the negative, though, I'm going to go to negative infinity. If this was going to negative infinity, I would also still be going negative infinity, because when I square negative, that becomes positive. Okay, then we get to limits at a point. What happens here, when I plug in 2, I'm going to get 0 over 0. So this tells me I can factor and reduce. So at the top, we're going to first factor out a 2. So you'd have like 2x squared plus x minus 6. Then, of course, this will factor x plus 3x minus 2. Bottom is x plus 2, x minus 2. So I factored out that. And we complete factoring. Reduce it. And then, once I reduce, I can plug in my 2. And I get 2 times 5 over 4. Okay, next topic. Definition of derivative. So the big thing with definition of derivative is just going to go over it and kind of apply it to make an approximation. The definition of a derivative is limit as h approaches 0 of f of a plus h minus f of a over h. This is the limit at a point. So my function is ln of x. So I'm going to do natural log of 6 plus a little number, so plus h, minus, my a is going to be equal to 6, natural log of 6 over h, and h I'm going to make a little number. So this was plugging into the definition. So x equals 6, I have 6 plus h minus ln of 6 over h to approximate it. Let h be a real small number like 0.001. Then I just punch this in the calculator, and you find is equal to about 0.167. So when you give our decimal answers, we're going to go out to 3 decimal places. That's what we're going to use as kind of a standard. That's what they use in calculus. On problem 3, power rule. So straight knowing our power rule. First one is pretty straightforward. We have 3 times 6, that's 18x squared. Of course, power rule is when you have x to the n, it's going to be nx to the n minus 1. So we get 18x squared minus 10x minus 1. For this guy, we need to rewrite it first. Well, this is 1/2 times 1 over x cubed, or 1/2 times x to the negative third. Now I can do my derivative. So again, negative 3 comes down, so it's negative 3/2 x. We subtract 1 from this. Negative 3 minus 1 makes this negative 4. And if you left your answer like that, just fine. Or if you wanted to rewrite it, it can be rewritten as this. But this answer right here is okay. Okay, so we have x to the 1/3. We got to rewrite this. Then it's 1/3 x raised to the, subtract 1 from 1/3. 1/3 minus 3/3 is negative 2/3. And if you left your answer like this, we're okay. But you might see it simplified out. Okay, next topic was tangent lines. So tangent lines. Equation of a line tangent to a curve, we just need to get a slope and a point. So the slope and point. Slope comes from the derivative, so I'll take the derivative and plug in -2. So my slope is going to equal 8. So I just took the derivative, plugged in -2, got +8. For the point, you plug into the equation. It says f of -2. When I plug this in, I get -8 plus 8 plus 7, so I get 7. Now, when you write your answer is kind of up to you. This is the way I tend to write it. I have a slope of 8, and I use point slope form in this way. I use it as y is equal to m x minus h plus k, because it kind of corresponds to what we did with shifting like parabolas and other kinds of things when we're shifting graphs. This is shifts left and right. It works opposite. This is shifts up and down. So I have a slope of 8. And it goes to the point -2, so it's x plus 2. I do the opposite, plus 7. That's an okay answer. Some of you seen point slope form where you see it as y minus the y value is equal to the slope times x minus the x value. That's an okay answer. Or if you want to put it in slope-intercept form, that's an okay answer. So it's all up to you. I just think one of these first two are the easier ones to use. Okay, question 5. So cannonball is fired from a height so that its height is found by this equation. We want to find the velocity of the cannonball when it hits the ground. Well, first thing you've got to do is figure out when it hits the ground. It hits the ground when h of t equals 0. So now we're going to choose a quadratic formula, plugging in, and don't need to see you actually punch it into the quadratic formula or doing whatever. I mean, when I've taught it in my classes, I've had students program the quadratic formula into their calculator. So what we're going to do is we're going to plug it in. So that like -100 plus or minus the square root of 100 squared minus 4 times -16 times 20 over 2 times -16. Then you're going to get two answers. You have -0.194 and 6.444. Well, the negative won't make sense, so we can eliminate it. So this is the answer we want. I want to know the velocity when t is equal to 6.444. So the velocity is the derivative. So I take the derivative, and I get -32t plus 100, plug 6.44 into that equation, and you're going to get a negative answer because it's falling. So it hits the ground at -106.207 feet per second. If I wanted the speed, it'd be the 106.207 feet per second. But it's velocity, so velocity does have sign. Okay, so those first 5 problems will all be like worth 10 points each. When you get to the next part where you're actually applying things a little bit more, we're going to be worth twice as much. So this one's using derivatives. We were given the derivative, and we want to find out where does the original function increase. We're going to justify our answer. First thing we're going to do is build a sign chart. So my critical points, because again, this is derivative, be aware of what you're working with. I have critical points at 3 and at -2. So I can build a sign chart. Now, if I think about this, as x gets really large, as x gets bigger, I'm going to have -x times x squared. It's going to be -x cubed. It's going to finish negative. This is a single root, so signs are going to change. Or I could test the middle right here by plugging in 0. If I plug in 0, I have 3 times 2 squared. That's positive. When you have a square, it's going to repeat. Now I could also test points. I could plug in -3 into the equation. Then I have 3 minus -3, that's positive 6. I have -1 squared, but when we square a negative, it's positive. So I'm at positive, positive. I'm looking where f of x is increasing. Well, f of x is increasing as long as x is less than 3. So from -infinity to 3, and we say since f prime of x is greater than 0. So that's your justifying your answer. There's 2 parts to justifying it. One is a sign chart or showing some testing of points. And this is the other part of it. So don't forget that part of it. Now, some are wondering about, what about -2? Do I include that? Well, if you wrote your answer as -infinity to 2, to -2, union -2 to 3, that's still correct. So, but if you did include the -2 in this one, it would be still okay. Okay, it says find the x-coordinate of any relative maximums for f of x. Okay, so relative max occurs when the derivative changes from positive to negative. So if I was actually thinking about sketching this, my function's increasing. So this is what it's kind of doing. I'm going to kind of sketch it over here. It's increasing, slope of 0, increasing, and then decreasing. Here's your peak. Your p cap is at -3. I don't know what the y value is, but I know that the p cap is when x equals 3. So max at x equals 3 since f prime changes from positive to negative. That's your answer. This is what you just need right here. Okay, first 2 parts are pretty straightforward. They're not going to be that difficult. Last part to take a little more work. We want to know, where is the function concave down? Well, I need to get the second derivative and find out where the second derivative is negative. What we need to do is first multiply out f prime of x so I can take its derivative. So I'm going to square this. X plus 2 squared. If you need to, do x plus 2 times x plus 2, but a shortcut. It's x times x. Multiply these two together and double it. So I go 2x doubled is 4x. Last term times itself. Okay, now I'm going to just distribute and gather my terms. So I had -x times x squared. That's -x cubed. And if I go to my x squareds, I have 3x squared minus 4x squared. Gives me -x squared. Go to my x's. I'd have 12x minus 4x. So that's going to give me 8x. And then just by numbers, it'd be 3 times 4, which is 12. So you can multiply it out, just FOIL the whole thing, gather your terms, but this is the ultimate what I'm going to do when I get it multiplied out. Now remember, I still have to take the derivative of this. So I get -3x squared minus 2x plus 8. I want to find out where it's concave down, so I'm going to find out where it equals 0. And just to make the factoring easier, I'm going to factor out a negative. So -3x squared, this becomes positive, this one becomes negative. Okay, so to get 2 numbers that multiply when I go over, I'm going to have -8. First number is going to be 3. I'm going to get a middle term of 2. So if I did 3x minus 4 times x plus 2, I'll get -4x plus 6x gives me positive 2x. Now, I'm going to look at my critical points. My critical points are at 4/3 and -2. This right here, when I'm above 4/3, this will be positive, this is positive, but I have negative there, so it's going to finish negative. I could plug in 0 if I wanted to. If I plugged in 0, I'd have negative of -4 is positive 4 times 2, so that makes this part positive. And I could even plug in another number if I wanted to, but there's no square, so the signs should alternate. So once you get one of these, you can figure out what the other ones are. So just plugging in 0 might be the easiest thing to do. Make sure that you find the correct region, and the signs tend to alternate. Okay, we're concave down when the second derivative is negative. So it's when x is less than -2 or greater than 4/3. So concave down from negative infinity to -2, and then from 4/3 to infinity since f double prime is less than 0. So don't forget this part of it. Now, inflection points. We'd have inflection points at x equals -2 and x equals 4/3. My reason is f double prime changes sign. That part's going to be important. Okay, this time we were given the graph of the derivative. So remember, this is our graph of our derivative, and I want to use this graph to figure out where I have relative min. I may be asking where the function is increasing. I could ask all kinds of different kinds of questions. We could even, at this point, ask about things like concavity and other stuff if we look at the slope of g prime. Okay, so looking at this graph, basically I've got a sign chart I can build. The graph is above the x-axis here, so it's positive. Then it dips below, so it would be negative. Then it's above, so it's positive. It's above right in here, so I go positive. And then positive over here. So I really went positive, positive all the way through. This is actually 0 right here, so I immediately put the plus there. But it's positive all in this region. So if I'm looking for where g is increasing, well, g would be increasing if x is less than -5 or greater than -1. I have critical points at -5, -1, and +3. Those are all my critical points. Okay, so we're going to try to determine the value of x where we have a relative min. Relative min occurs when the derivative changes from negative to positive. So I went from negative to positive right here at -1. So g of x has a relative min at x equals -1, but it did say justify your answer. So to justify my answer, you say since g prime changes from negative to positive. Okay, we want to approximate the equation of the line tangent to the curve. So at x equals -4. So a line, again, needs a slope and a point. My slope is going to be the derivative at -4. G prime at -4, well, I got to look at the graph. So I look up where is -4, and I figure out what is the y value here. Well, that tells me right here my slope, then my derivative at -4 is equal to -3. So I have a slope of -3. Now I need to get a point. Well, they gave us the point up here in the very beginning of the problem. They call it the stem of the problem. So there's my point. Then I'm just going to put it into my point slope form. So I get -3 times x plus 4 plus 7. And again, you can write this in a variety of different ways. Other kinds of questions, they could ask you, where's the graph concave up? Well, then I got to look for where is g prime increasing. Well, that would be increasing going from -3 to +1 and from 3 to infinity. So there's different kinds of questions you could possibly see. Points of inflection is when the second derivative changes sign. So I look where the slope of this graph changes signs. So it changed signs at -3, +1, and +3. Okay, this one's probably one of our harder ones. We're going to try to sketch a graph based on all these clues. So we're going to read through all the clues first, and then we'll add the pieces as we go. So I know the function is not defined at x equals 2 and x equals -1. Well, that means it could be an asymptote or it could be a hole. As x approaches infinity, the function is going towards 0. So I just know it's going to cling to the axis as I go to infinity. As x approaches -1, okay, that's where I was undefined, I get g of x equals -2. Okay, there's our hole. As x approaches 2 from above, we go to positive infinity. As x approaches 2 from below, we go to negative infinity. Okay, there's an asymptote. So I know at 2, I've got an asymptote. And I have a hole at the point -1, -2. So that's just getting my initial information going. Function has no real roots, has a y-intercept at -3, so I'm going to have a dot down here at -3. Oh, and that also has no real roots, and I've got it so that as x approaches 0, I'm going towards 0. And then I've got this dot right here. Now, in terms of graphing this, there's lots of correct answers. The one kind of answer I think that makes most sense is to draw this one going down through the hole and just heading like this. Now, I don't have to have it go towards this. I could even have it come up and then turn back down because it doesn't say negative infinity what it does. That's why you can get different kinds of answers. Here, I need to make sure, though, that I'm heading towards positive infinity. I know I don't have any roots, so I got to make sure it stays all in here and then approaches this. So the easiest way is to just do something like that. I didn't do the prettiest of graphs right there. There we go. So any kind of a curve that might look like that. Okay. Now we're going to find the function based on the graph. So let's take a look at our clues right here. Well, I have an asymptote at -2, and that's at x equals -2. At y equals 2, I have a horizontal asymptote. I have a hole here at the point 1, 3. I have a point over here at, looks like -3, -1. So let's starting with different parts. Okay, I have a hole at x equals 1. Well, when I put my function together, that means I have to have x minus 1 cancel out. So that will make a hole. So I'm just kind of building as I go. We have an asymptote at x equals -2. Well, that means I have to have x plus 2 on the bottom. I have a horizontal asymptote at y equals 2. So as x goes to infinity, dominant term will be on the bottom. This would go to 0. So the easiest way for me to get this asymptote is just to add 2 to the equation. Okay, now this gets most of it. There's one other component. I may have a number out in front of the x minus 1. Because I know when I plug in after I reduce this, it has to go to the point 1, 3. Because my hole is at 1, 3. Or I could even use this point right here to try to figure out what that value is. So I'm going to add a value, and basically this is limit as x approaches 1 equals 3. I'm going to put an a, because this constant right here could be out there, because I know this part, all of this will go to 0. There's other ways of doing this too. You could actually add in other components to make it so that you can have a single fraction, but I just think it's the easiest way to approach this. Okay, so that means as x approaches 1, I'm supposed to go to 3. Well, this part I could reduce, and then I'm going to plug in 3 into the equation. So I have a over 3 plus 2, a over 1 plus 2, because as x approaches 1, plus 2 has to equal 3. So I have a over 3 plus 2 equals 3. So a over 3 equals 1, so a has to equal 3. And there's my equation. Now I can actually act as a check if I wanted to. If I did everything correct, this point should work. So if I plug in -3, I should get -1. So if I plug in -3 into my equation, I forgot, basically again, I'm going to cancel those off, which makes it a little bit easier. 3 over -3 plus 2, that's -3 plus 2 does equal -1. So that does confirm it. So this is my answer. This is acted as a check. I could have done the same thing if I wanted to use the point instead of the hole to figure out what that equation was. Okay, last problem is the big one. This is going to do a full function analysis. So we're going to go through each of the parts. First, we're going to look at just k of x. So we want to find its roots. Well, easiest thing to do is test numbers like 1 and -1 to see if they work. The possibilities are going to be 1, negative 1, 1/2, negative 1/2, 1/4, and negative 1/4 are the rational roots. Those are potential ones. But 1's going to be pretty easy. If I plug in 1, I get negative 4 minus 15, that's negative 19, plus 18 plus 1. So negative 19 plus 19 equals 0. So I know k of 1 equals 0. Well, I already know that one of my roots is going to be at x equals 1. So if I already know x equals 1 is one of my roots, I could just use synthetic division to figure out what is left over. So I move negative 4 down. Then 1 times negative 4 is negative 4. I get negative 19. 1 times negative 19 is negative 19. Add those together, I get negative 1. Negative 1 times 1 is negative 1. Remainder is 0. That means that I've got this quadratic, negative 4x squared minus 19x minus 1. So x minus 1 was one factor, and then we had this. Now what I'm going to do is I'm going to factor out again negative before I use the quadratic formula. So that makes this 4x squared plus 19 plus 1. So I've got a root at x equals 1, and then what the quadratic formula gives me from this. So I can just punch it into the quadratic formula, and my roots will be at 1. When I evaluate this for the 2 points, I get negative 0.53. That was negative 19 plus the square root of this stuff over 8. And then negative 19 minus the square root, whatever that came out to be, over 8 was negative 4.697. Okay, so we have our roots. Next thing we wanted to ask about was the y-intercept. That's easy, just plug in 0, get 1. Okay, then we want to look to our limits to infinity and negative infinity. So as x goes to infinity, there's not really much work to be done right here. You just got to think about it. Okay, well, I've got negative 4x cubed. That's my dominant term. So as x gets really big, it's going to end up being a real big negative. So this is going to go to negative infinity. As x approaches negative infinity, well, x cubed, when I plug negatives in here, that becomes negative. So I have negative times negative will make it positive infinity. Okay, so that does our analysis just of the original function. Now I'm going to put in some of the pictures onto the graph just to kind of see where things are. So right now we have an unscaled y-axis. I did bother to put a scale onto the x-axis because I know those values will be okay, but I'm not sure how to scale the y-axis at this point. So we have our roots. All right, x equals 1, negative 0.053, and negative 4.697. So I'll put a dot there at 1, close to the x-axis, and this is around a little bit past negative 4.5, so right in this range. Okay, we have the y-intercept at 0, 1, but I haven't scaled this, so I'm not going to put a dot there yet because I don't know where the scale is, so I'm just going to kind of ignore it for now. Then we have our limits to infinity. Well, as x gets really big, I'm going to go to negative infinity. That just tells me that as I head in this direction right here, I'm going to be heading downward. So I just know I'm going to be heading down somewhere in this area. As x approaches negative infinity, if I go to the left side, I'm going to be going towards positive infinity, so it's going to have to finish up. So that gives me a little bit of guidance about where my graph's going. So I know my graph's going to do something where it's going to have to come down through here, go through this point, and then come back down. That's most likely what's going to be happening. There's other things can be weird happening in between, so we're going to find that out when we look at the derivative. Okay, so now, so this one right here, we're going to take this derivative. I got negative 12x squared minus 30x plus 18. 6 goes into all these, but I'll factor out a negative 6 to make it a little bit easier. Okay, 2x squared plus 5x minus 3. If I do 2 times 3, I get 6. So two numbers that multiply to give me 6, but add to give me 5. Well, I'll multiply to give me negative 6, but add to give me 5. Well, I'm going to have basically, when I start to think about it, you can actually, there's ways of going over and doing these factoring, but I think it's easier just to build it out. So I have 2x and x. So I just got to make sure I've got positive 6 minus 1 gives me positive 5x. And I get all my values here. Okay, so critical values are x equals a half and x equals negative 3. So I'm going to build a sign chart. And in this case, it might be just really easiest to do is just to plug in 0 to see what happens. If I plug in 0, which is right in between, I'm going to get 18. Just plugging in 0 right here. So this section right here is positive. There's no squares on these. So that means the other two should be negative. You could plug in points to test it. I could try it with plugging in like 1. If I plugged in 1 in this equation, I would have negative 12 minus 30. That's negative 42 plus 18. That's negative. So I could test it. But once you get one of the points, you can usually figure out the others. Okay, so I'm going to forget where's the function increasing, decreasing, relative mins, relative maxes. Okay, so starting with this, function increases going from negative 3 to 1/2 because k prime is greater than 0. So where it's positive. K of x decreases when x is less than negative 3 or x is greater than 1/2 since k prime is less than 0. We have a relative min at x equals negative 3. So this derivative changed from negative to positive. And if I want to find the x coordinate, which I do, take negative 3 and plug it into the original equation. That's where the negative 80 comes from. So that's my relative min. This will help me to scale my graph now. So I'll have that graph go by tens on the y-axis. We have a relative max, derivative change from positive to negative over here at 1/2. So I take 0.5, plug it into the equation, I'll get 5.75. So I have relative max at 1/2, 5.75. And my reason is since k prime changes from positive to negative. So don't forget your reasons on each one of these. Okay, so now we're going to plot this information. Okay, so now I scaled the graph because I know that it had a relative min at negative 80. So I'm going to start with this. So at negative 3, negative 80, I'm going to plot my relative min. Then my relative max happened at 1/2 and 5.75. So right in this range is my relative max. Okay, now I'm looking for the graph increased and decreased. So I'm going to kind of like build almost like a sign chart on the graph. So it happened at negative 3 and 1/2. This is where my critical values are. We knew it was increasing from negative 3 to 0.5. So it's increasing in here, so I'm going to write increasing. It was decreasing on the other two sides. So I'll write decreasing and decreasing. So that means my graph goes down. I could actually pretty much sketch the graph right now if I wanted to, because it goes down, comes up, goes back down, and I can see it matches everything. So whatever you do in your analysis part where you're going over and actually calculating out the different parts of the derivatives, they should match your graph. It should make sense. Okay, let's look at the second derivative now. So here was our first derivative. Now we're going to take the derivative again, and I get negative 24x minus 30. I'm going to find out where this equals 0. So I get negative 30. Well, I get, if I do 30 divided by negative 24, so it's negative 30 24ths. That's negative 5/4, or you can do negative 1.25. You can use decimals, that's okay too. I'm going to build a sign chart again. Well, if x gets really big, this is going to make it more and more negative, or I could even plug in 0, which would be over here, but I could tell it's going to finish negative. then the other side is going to be positive. I plug in a number that's less than negative 1.25, like negative 10. I get positive 240 minus 30. So it's positive. Okay, so concave up from negative infinity to negative 5/4 or negative 1.25. The reason, since k double prime is greater than 0. It's concave down when x is greater than negative 1.25, since k double prime is less than 0. That's what makes it concave down. The last thing for our analysis is a point of inflection. I have an inflection point at x equals negative 1.25, and again, to find out where that point is, we always, any point on the graph, we plug into the original equation. So a point of inflection at negative 1.25, negative 3.37.125. And my reason for point of inflection is since k double prime changes sign. It's not since k double prime is equal to 0. Because sometimes when the second derivative equals 0, it doesn't change signs and it's not a point of inflection. Okay, so now we just got to finish our graph. Okay, so my inflection point was at negative 1.25, negative 37.125. So I'll plug that in. Then here's my critical point. I was concave up from negative infinity to negative 1.25. So concave up. Over on this side, I was concave down from negative 1.25 to infinity. Now my last thing is I'm just going to sketch the graph. And there's my graph. So you get the basic idea of just what we're doing for each of these parts. So on the final, when you should expect, don't expect to see, think you have to get 90% or better to get an A. It's not going to work on that. This is a relatively sophisticated test. So we're looking at probably, for grades, we're looking at probably 80% is where the A's would start. 65% would be for B's, 50% and above would be for a C. So don't freak out if you get stuck on a problem. That's okay, because you should be able to be okay with getting a decent score if you keep track. But the test will be very, very similar to what you see here. Okay, good luck, and hopefully everything goes out well.